Then we move to the next presenter, next speaker, Professor Petros Patias from the University of Thessaloniki, Greece. Petros, the floor is yours, and it's all about complexity, object complexity with model complexity. Thank you, Petros.
Thank you, Marianos. Can you hear me? Can you see the screen?
Crystal clear.
Okay.
On image. Thanks.
So, good afternoon, everybody, and thanks for the invitation, Marianos. We're going to speak about object complexity versus model complexity. Now, defining complexity is a complicated issue of its own anyway. Defining complexity in an effective and productive manner is even more difficult. So my presentation today is actually intends to initiate the discussion, bring up this kind of issue. And since this is part of online research, I have to say that I don't have all the answers yet, okay? So the main target today is to bring up the issue and initiate this type of discussion. Now, if time permits, otherwise Marinos will cut me off anyway, we're going to discuss about what is the limiting factors of 3D digitization process today. That is, what is the limiting factor of the technology and the applications. If we actually need a definition of object complexity, and if so, then what would be the characteristics of such a definition? Then we need to define the complexity and we need to quantify it and to connect it with quality, technology, and the purpose of digitization. And then finally, we're going to synthesize all the above in a decision-making workflow, just to show how these things can be taken into account to plan the data acquisition phase. Now, let's see what is the limiting factor of technology. I mean, what the technology has to offer us today. As you know, microscanning can give us a resolution or an accuracy up to 1 micron. We can easily get half a centimeter with photogrammetry, and also very easily half a centimeter with laser scanning. Using GNSS topography and surveying, we can get down to 1 centimeter, which is pretty enough. With using drones and UAV imagery, we can get easily 2 centimeters. And with satellite imagery, we can have a resolution of 30 centimeters today and going down into the future. So this is what technology offers us today. Let's see what we actually need in different types of applications. Now, suppose that we have to 3D print a replica of a small object, 1-to-1 scale, okay? Or we need to have a digital archive at the maximum resolution of this small object. Then we need to have an accuracy or a resolution of 2 microns, and that's enough for all these applications. Or in case we have a large object, then we don't need something in less than 1 centimeter. Also, if we just want to view the 3D object in a web application, and since at the viewing distance, 200 microns is the resolution of our eye, then this is the actual resolution that we need. So comparing these two tables, we find that the current technology supports even the most demanding current needs, whereas the mainstream applications can be easily met by rather relaxing technology. So the first argument that we have is that the focus should be shifted from the data acquisition to the object modeling. Now, if we go to have an idea of what the term complexity is about, then it seems it is a rather trendy term. The number of hits, for example, obtained by searching the complexity in 3D through Google or Scholar Google are around 157 million hits in Google, and we can take it as a proxy for overall diffusion of the concept. Whereas in Google Scholar, we can have almost 3 million hits, which can be taken as a proxy of academic interest. This means that this, let's say, term is rather trendy now. Now, let's have a look of what we mean actually when we say something is complex. And I have for you 3 examples here. I'm running them, all of them, at the same time. This is quite a complex one. That has to do with a cave, and the whole thing is a 3D digital replica of the cave. As you see, it's very complicated. This is a bunch of rocks in Greece, in central Greece, and on top of every rock, there is a monastery. So here we have also multi-resolutions, a different resolution for the area, another one for the rock itself, and the third one for the monastery itself. So as you see, something that can be very complex, either because they have a lot of points, or can cover a large area, or they can be described only by multi-resolution. Now, going down to smaller objects, I gave you some examples here. This is a very famous Cycladic art from the Aegean Islands. These are coming from an excavation of Neolithic settlements in North Greece. And these are made of, it's a spoon made of bone. And this one is from the Museum of Contemporary Art in my town. Now, here also we have very, very high resolution, an ultra high resolution. Although the objects are small, then the resolution is very large. And this doesn't have to do with the anaglyph or the 3D of the surface itself, but by the number of the points that we need to describe it, or the number of detail that we need to have it. So, to make things even worse, and since up to now we were dealing with only monuments and archaeological sites and museum objects, we need to take into account that cultural memory also includes photographs, different prints, archival documents, sounds, and audiovisual material, and as well as intangible heritage. So this makes things even more complicated. So, do we actually need a definition, okay, for object complexity? Object complexity is, of course, very important since it has various aspects of 3D digitization. Therefore, it's not surprising that the term complexity is quite often used in cultural heritage documentation practice. What is not expected, though, is that the fact that it is always described by, it doesn't have a clear definition. It is described by qualitative terms. It has no subjective methodology. And also there is no connection to quality, purpose of use, and other, let's say, restrictions. So in other words, the tooling of the object complexity, as far as decision support tool, has always remained a gap. So what we need to do here is we need to define object complexity as a value of its own, which should be estimated subjectively and before the measurements, before we make the measurements, and also it should be connected with intended use. So my argument here is that, again, we need to shift our attention from the object complexity to the model complexity. This means that our focus is not the complexity of the real object per se, which is connected to the data capture phase, but the complexity of the produced model, which is connected to the data processing phase. Let's take an example to make it more clear. Okay, suppose that we have a statue of 3 meters high, let's say, of a rather complicated marble surface. And the purpose is to digitize it in 3D and to use it into a virtual museum of Roman history. This means that the produced model will be seen on a computer screen at a maximum 3 times the zoom factor, and that means a maximum scale of 1 to 50 of the original statue. This translates to a model with a dimension, the maximum dimension will be 6 centimeters, that makes 3 meters into 1 to 50 scale, which will be zoomed by a factor of 3. Thus, the final model should be seen in a full detail corresponding to a visual object of about 18 centimeters high. Now, this should be able to be examined seamlessly at a normal viewing distance, which corresponds to a typical optical resolution of 200 microns. Dividing the maximum dimension of 18 centimeters by this resolution, we end up of 9,000 surface-defining triangles of a maximum dimension of 200 micron sheets. And this is the model fidelity as defined by the purpose of the 3D digitization. Now, if we go back to the original object, and let's assume that the modeling process degrades the fidelity of the original measurements by a relaxation factor of, let's say, 2. That is, the original measurements are smoothed and generalized, which is normal practice, through the modeling phase, so that they lose half of their original accuracy of representation. So in order to make sure that the final model keeps its aimed characteristics, we need to make original measurements twice as accurate than the model specification. But we need twice as many triangles, that makes 1,000 triangles to describe the object surface. Now, if we divide the object dimension of 3 meters by the number of triangles, we end up with a resolution or a maximum dimension of the triangle side of almost 1.5, 1.5 centimeter for the 3D digitization measurements. Now, what is the conclusion? The conclusion is that no matter what the complexity of the original object is, we will not be able to see smaller details or measurement errors, of course, than say 1.5 centimeters on the object surface. This is the actual complexity that matters to us, and according to this, we may plan the use of the optimum technology and the recording strategy. Now, if we, let's say, summarize what we have up to now, is that the first one is that the complexity will determine to high degree the technology to be used. For example, it is quite difficult and unproductive to use photogrammetry to record the complexity of a cave, whereas laser scanning is a suggested technology in this case. Complexity is the missing connection between the quality and the purpose. For example, although it's possible, it is useless to use UAV imagery to map a large surrounding landscape or an archaeological site, whereas satellite imagery is much more preferable. Complexity imposes restrictions on both the technology and the intent in use. For example, surface transparency violates basic photogrammetric rules, preventing the use of this technology. Also, low reflective radiation of certain surface materials poses restriction to the laser scanner as well. Finally, complexity connects quality, accuracy, and completeness, as long as it expresses parameters like object size or resolution requirements. For example, a complex interior calls for a fusion of technologies, Douglas mentioned it before, of course, exploiting the merits of each one, while measurement requirements for multiple resolutions are often dictated by multiple use of the same 3D acquired material. So complexity is an abstract term that may have different, let's say, contents in different disciplines. For example, you can meet terms like computational complexity, Kolmogorov complexity, entropy, statistical complexity, network complexity, and so on and so on. And sometimes complex and complexity, complex and complicated is used without clear distinction between them. So roughness metrics, which is normally used in mechanical engineering, is something that is more closely to what we mean when we say, when we define complexity. So what is important up to now is that the roughness, okay, or the surface complexity is scale variant, and it is assessed at a scale which is meaningful with respect to the specific application. That's something that we need to have in mind, because this is the point where our scale comes in. So summing up, the definition of the object complexity should have the following characteristics. It should refer to both data capture and the data processing. It should be calculated subjectively and before the data acquisition, and connect to quality, technology, and the purpose. Now, let's see how we can measure complexity. So, assuming that complexity can have 3 different parts, or maybe more. One should have a connection with the geometry, okay, geometry or structural complexity. The other has to do with the surface or the texture complexity. Another has to do with the material complexity. And of course, there are other parameters coming into the picture. So having to do with structural complexity, then this refers mainly to the degree of detail that we would see. And this is normally represented by the number of triangles and of course, which has to do with the size of the object. So it is clear that the absolute number of triangles does not reflect the object complexity, okay? Because for big objects, of course, we have many triangles. For smaller, we have less. So the number of the absolute number of triangles does not reflect the complexity itself, but only the relative number is useful. So we propose to use the ratio of the numbers of the triangles per unit surface instead, and not the absolute number of the triangles. Surface or texture complexity has to do with the red, green, blue, and alpha values that mean the opacity. Material complexity has to do with the physical characteristics. And of course, we have other parameters as well, that is environmental, motion, and so on. Now, if we try to make a table out of it, then and suppose that we have 3 or 4 different degrees of complexity, that means low, medium, high, and ultra high. And then we have movable or immovable objects. And also we, let's say, classify the different complexities as geometry, surface, material, and so on. Then what we need to define is the number of triangles per unit surface and the minimum triangle dimension. Here, I'm trying to put some threshold value for that. For example, for immovable objects, ultra high complexity means that we have a resolution of less than 1 millimeter, okay, for immovable. And the low complexity means about triangles of order of 10 centimeters. Whereas for the movable objects, ultra high means less than 100 microns, and low complexity means about 1 centimeter. Same threshold values could be defined for the surface and texture complexity, for the material complexity, and so on and so on. Now, an idea of how to visualize this is the following. We can visualize the complexity as a composite indicator. That means we can have a kind of spider diagram where low, medium, high, and ultra high is the number found of all complexity ratios, let's say. During, I mean, inside this visualization process, you can have different, let's say, parameters for complexity. And here, for example, we have 3 different objects: the yellow, the green object, which is the less complex, okay? The yellow, which is the medium complexity, and the red one, which is a high complexity. Now, if we calculate the area of this spider diagram for every object, let's say, we come up with different numbers. And these numbers actually reflect. Now, these numbers do not have a physical meaning. It has to do only with the area of the graph, but it reflects to the complexity of the different objects. And as you see here, object 1 has much higher area value than the green one, which is the lowest. Now, if we also compute, let's say, the standard deviation of the different parameters, here you can find that these numbers actually reflect the similarity of the component. That means, of course, the red object is the most complex of all 3, but is it complex in all parameters? Okay, so here it seems that this high standard deviation means that there is non-similarity in the different components. Whereas the most, let's say, I mean, the object who has more or less similar parameters, similar complexity parameters in all these cases is the yellow one, okay? So actually here we have 2 metrics. One metric has to do with the complexity itself, and the other has to do with the similarity of the components. And also we have a graph, which is rather easy to define and visualize, that visualizes this kind of complexity. Now, if we go back and try to connect complexity with the quality, we need to have in mind that not long ago, quality parameters were used to reflect the 2D terms. It is worth noting that data acquisition technologies are, let's say, in two different spaces. We had it in 2D and we have for plane surveying and the leveling, and we have in photogramming and so on, or the cross sections, but we always referring to 2D and not to 3D. Things, of course, have changed since then, and now we are in the process that the current acquisitions are done in 3D. So when we say quality, we mean quality in 3D. Okay. Now, regarding the geometry, and of course here again we have the degrees of complexity and the movable and the immovable objects, but we have geometric accuracy, radiometric accuracy, and completeness. When we say geometric accuracy, here, what we mean actually is the accuracy, of course, and the precision. The precision has to do with the instrument that we use, and the accuracy has to do with root mean square errors of your errors. Here again, I try to put some threshold values that has to do, of course, with the resolution that we saw before. So my basic assumption here is that the resolution should not differ from accuracy, since it does not make sense to collect denser points than the accuracy level. Okay. A third part has to do with the technology itself. Okay, and there we have a number of technologies that can be used, like tactile technology, topography, photogrammetry, laser scanning, satellite remote sensing, and more specialized technology in different cases. So in this case, not all technologies are good in all different complexity levels. So we need to define what kind of technology is more preferable. Okay, and of course here you can see that in many cases, okay, it's a cluster of technologies that can be used, or fused technologies can be used at the same time. Finally, the purpose of the 3D digitization. This defines, of course, this is the basic thing. This is something that we need to start from. Okay, so the first thing that we need to think of is what is the purpose of the 3D digitization, and then we can go backwards to the data acquisition, the technical specification. Here, I was trying to, let's say, to classify the level of the 3D digitization in 3 different levels. And that has to do with the accuracy and the resolution needed for every level. So the most detailed level, okay, there is a preliminary level, and of course there is a reconnaissance level. Now, I suppose these are the thresholds that I used already in the previous table, as you see. And here, lambda 1 is the relaxation factor. Okay, as you see, the complexity of the object is the same everywhere. The complexity of the model is what changes. So here, the complexity of the model is exactly what we needed from the previous table. So here, the relaxation factor is 1. That means what we need is what we get. Here, for the preliminary level, we can relax our accuracies. That means we can make it twice as worse, let's say. So lambda 2 is 2. And here we can make twice more as worse. That means lambda 3 is 4. Okay. That means if we need to digitize something very accurately, this is the level. This is half the accuracy, and this is 1/4 of the accuracy of the whole thing. Now, I will give you some examples here. For example, here it's a movable object. It has a resolution. Let's say it is it's high, medium, and low resolution. Here I come up with a minimum triangle dimension of 300 microns, and here is 800 microns, and here is 0.4 centimeters. That comes up with more than 666,000 triangles. Here we need 20% of those, and here we need only 10% of those. Just to have a look of how different, let's say, levels of complexity and, of course, levels of data acquisition is being used. Of course, we can see other examples as well. This is another movable example of ultra high resolution of 48 centimeters high. Again, the triangle, the minimum triangle dimension is 300 and so on. I will not take the time to show you other examples, but you get the idea of how the degradation of the complexity is being done. However, we have other cases with very ultra high complex objects like this one, where the surface complexity is due to very fine texture like this, or very narrow wires like this, or due to the opacity of the object like that. I will show you what I mean. So here, this object is made of glass. It's made of very fine wires. This one is made also of very fine wires. So here the complexity has to do with the material and the structure of the material. So if we would like to sum up the whole thing and try to synthesize and come up with a decision-making process, let's say workflow, I would go like this. First, we need to define if our object to be digitized is movable or immovable. Then we need to define what the purpose is. And from the purpose, we get the requirement for the modeling. Okay, we need to define if it is a preliminary or a reconnaissance type of surveying and so on. Then we come up with the minimum accuracy needed for this kind. From those, we can apply a relaxation factor that has to do with how much degradation we feel that the modeling phase is putting into the process. Then from that, we come up with the accuracy, the resolution, and the number of triangles required for the data capture. And this gives us the technical specification of the 3D digitization. From there, we can also add up other restrictions like accessibility, time, budget, and so on. And then finally, we come up with a suite of the suggested technologies. Here, from all these technologies, we need to come up with which are the technologies best suited for this 3D digitization. And that comes as a decision-making workflow that comes, starts with the object, goes through the model, and then comes to the object again, gives the technical specifications, and then you add up different other factors that come into the process, and finally you get the class of the suggested technology. And this is the idea of the whole discussion: is how to define complexity in a productive manner that will give you, let's say, finally a workflow to work with. So, just to sum up what we have talked about today, is that the current 3D digitization technology is able to support digital applications beyond the current mainstream application. The focus should be shifted from the data acquisition to the object modeling. The definition of the object complexity should refer both to capture and the modeling. It should be subjective and should be estimated before the data acquisition. Also, it should be connected with the technology and the purpose, and should provide a meaningful tool for planning both the data acquisition and the modeling. Now, the complexity can be visualized as a composite indicator, and the connection to quality, technology, and purpose of use should be clear and lead to a productive and decision-making workflow. So this is what I had for you today, and thank you again for your attention.
Yeah, Petros, thank you very much. If I may ask our attendees for any kind of remarks, comments, questions, we still have enough time for discussion. Of course, we can move to the next presenter if there are no comments or any responses from the auditorium. And then we will leave time at the end to discuss. There is one from Fodis Larokabis. Fodis, your microphone, please, is free to use it. What is the preferred approach for virtual reality applications? This came now in. Petros, for your complexity probably.
Oh, so the question is for me. Now, virtual
I
reality.
think so, because just arrived here.
Yeah, okay.
So this didn't mention for which speaker the question was.
Okay, thank you for this. Now, virtual reality is, I would say, is not of the most complicated applications, okay? Because it is intended, the use of the 3D object there is intended for viewing mainly. So that means the resolution is not more than 200 microns or around that, which means that, of course, the data volume is very big there, okay, depending of how the objects are, how big the objects are. But the complexity which is involved is not that much. So it depends, of course, if the question is what kind of technology is suggested, okay, you should go through the diagram to find it out. But mainly, if you look back of different applications, that you see that for the small objects, mainly laser scanning is being used. For the medium-sized object, photogrammetry has been used, also connected with other technologies. If you go to the more complicated or let's say interior spaces, then laser scanning is more preferable. If you go and into the high buildings, then of course different technologies should be used, because for inside, let's say laser scanning is more preferable. From outside, maybe photogrammetry is more helpful, but then you need UAVs also, because you need to fly on top of the buildings. So in all these cases, different technologies are being suggested up to now. But again, the complexity required there is not that much. So the concern is not the complexity of the object here. The concern is the volume. That is as far as I could say.